All right, we're now officially recorded. I'm going to pause it, go ahead and work on this problem. Okay, so this one has a wrinkle. And pretty much everything in AP chemistry always has a wrinkle. That's why it's not very fun. All right, so here we go. You may recall the first thing to do, we converted the percents to grams. Then you divided each one by their molar mass. All right, we get three answers here. I don't remember what they are. What's this first one? Someone help me out. 3.41. Okay. This one's 4.58. And this is 3.41 also, correct? Okay, so we go grams, then we divide by their masses off the periodic table. Those are called the molar masses. Then we get these answers. The next step is to take all the answers and divide by the lowest answer of them all. And this is 1. This is 1. And this is pretty much 1.33 or 34 something. Right? Okay. The wrinkle is what to do when these are not all whole numbers, because they have to be. I can't put a 1.33 as my subscript, so this is what we do. It's pretty simple. If one of them is not a whole number, you have to multiply it by some number to make it a whole number. So, how do you make 1.33 a whole number? Times it by 3. But in math, if you do something to one thing, you have to do it to all things, right? So you have to, whoops, we already did before. So you have to convert or multiply all of them so they all become a whole number. And now you have your formula of C3H4O3. Did I do that out of order? Go ahead. What? This is just simply the amount of moles of C that was present. The amount of moles of H that was present. Well, sorry, it was here. I should be circling this one, not that one. The amount of H that was present, the amount of O in moles. Moles we'll talk about a little coming up, but moles are the way that one thing can talk to another thing. It's our base that we function all of our math upon. Okay, raise your hands if that made sense to you. Okay, that's pretty much mostly everyone. All right, let's take 30 seconds and maybe help clarify some stuff. 0 people in first hour are reading the book. How many people in this hour are reading the book? 1, 2, 3, 4, 5. Okay, that's a lot better than 0. That's only 5 out of 42 people, though. That's pretty much 1/8. That's pretty poopy, right? You need to read the book. B-time has made our kids lazy. It's made teachers better, but it's made you guys lazy because you think, well, if I don't get it, he'll fix it for me. And I know some of you are struggling and you're trying really hard. Some of you are confused on what is homework, what isn't. So let's take a minute and explain the structure of this class one more time. So, and I know it's confusing because I'm starting to develop a second thing while you're in. But the first thing that you should do to wonder what's going on in chemistry is go to AP Chemistry. When you go to this home page, you have the calendar. I've been surprised how many people have been surprised that there are quizzes on a day. The quizzes are on the calendar. The homework is due based on the calendar. So here's Monday. Today we're going to talk about stoichiometry and combustion analysis. Homework section 2 is due. That is tomorrow, right? All right? And you're like, well, I don't know what homework section 2 is. You have one of two things you can do. You can go to chapter 3, and it tells you you have homework problems, Black Book Problems PDF, homework part 1 form right here. So here's the PDF with all the problems. Okay? And then you have homework form right here that you can fill in. That would be for chapter 3, part 1. It was 11, 13, 17, and 19. You didn't have to do every single letter to turn in, but you had to do a lot. You hit submit, and I get those. That is your homework. All right? You can get this same information in Guru as well. So tomorrow, homework part 2 is due. So it would be 25, 33, 39, 45, and 53. These will be a little tricky. Each of the following use proper significant figures and units in your answer. It's not balancing right now. It's what we're doing right now. It's more math. So if it asks you for a mathematical value or numerical value, you have to use significant figures. All right, so what numbers are due tomorrow? It tells you on the page. All right. I guess it was right there on the top of that. I apologize. It's right there. Okay. So those are your homework. If you go to Guru, you can see the same thing, just in a little different format, because I'm moving from that to this. I don't even know if it's worth my time, but I'm going to see. All right, the administration is where you would find your articles. Black Book Problems 1, Problems 2, Section 2 form, and it takes you to the same place. I did discover this online textbook, and it's not even breaking the law. It was developed by which college? UC Davis. It's your textbook online. I put that on there as well. So, what is due will always be on the calendar. When it's due will always be on the calendar, and you can find that in 2 places. If you miss a class lecture, you can go back. So we're still in chapter 3, but now, so let's say you're Brendan and you missed balancing day 1. It's probably blocked here, but this is just class, just like I'm recording right now. Okay, so anyway, there's that stuff. There's a lot of resources in this class to help you to do well. I was really let down by first hour that 0 people are using it. I am not the only way that you can learn AP Chemistry. And if all you do is depend on me, you will not pass the AP test. You have to use your book. You have to use online resources. You have to use your friends. I'm blown away how many people still haven't even bothered to memorize polyatomic ions. They're like, well, I don't know how to name. You're like, why? Well, because I don't know the ions. You've had those since the first day of school. Like, you have to put in effort in this class or you will not do well in this class. All right, finding formula from percentages. That's what we just barely did. Find formula from combustion analysis. That's what we're going to do now. But in order to do that, I'm going to go back and we're going to introduce this idea of moles. Okay? We may have talked moles a little bit already. If you watch the online videos for this, it might make sense. If you had chemistry last year, this should be very, very, very simple. All right? Moles, those are the things that we're going to convert everything to so everything can talk to each other. You all right with that idea? All right? So, in order to speak the same mathematical language in chemistry, we have a standard unit that can link masses of one substance to masses of another. This is the mole. All right? This is kind of dumb, but maybe you have 100 kilograms of wheels. And you want to know how many kilograms of bikes you can make out of that. In order to know the answer to that, you have to know a few things. What do you have to know? You have to know the mass of one wheel, right? You have to know the mass of what? A bike, right? And you need to know one other thing, and that's the ratio of wheels to bikes. What is the ratio of wheels to bikes? 2 wheels to every 1 bike. And we could get that from a balanced reaction, right? It's weird, but look right here. 2 to 1. We're okay with that, are we not? In chemistry, this 2 and that 1 is a coefficient. We've been balancing with coefficients, right? In chemistry now, you need to know that our coefficients are the molar ratios. It's the amount of moles compared to the amount of moles of something else. It's not that hard, all right? A mole, like this slide will say, is equal to that big freaking number. It's 6.02 times 10 to the 23rd anythings. A mole is just like a dozen. It's a word that means a number. Just like we can have a dozen of anything we want, we can also have a mole of anything we want. So in the example right before, you could say you had 2 moles of wheels to every 1 mole of bikes. And if that's confusing, think about it as a dozen. You need 2 dozen wheels to make 1 dozen bikes, right? Because it was a 2 to 1 ratio. All right. Why do you care? So here we go. We've been using moles all along. We didn't really know it. The numbers we use for coefficients are listed in moles. Moles now give us a way to compare apples and oranges or sodiums to chlorines. There's no direct math link between sodium and chlorine in grams, because grams is what we measure. But there's not a ratio there, like there is, but not that we're going to worry about. So what we do is convert everything to moles first, because then they compare. I know that in this reaction, no matter what I do, every time I do it, the amount of Na is twice as much as Cl2 every single time. So if I can take my grams and I can convert them to numbers of that, then they can start talking to each other. Okay? This will be our week-long activity. Today I'm going to introduce this and then do something that may not seem to even make sense with this, but it goes together, I promise. All right? Moles gives us a molar ratio that can be used in what we call stoichiometry. One of the greatest chemistry words of all time. That is Latin for fun with numbers. If you believe that, you should transfer out. All right? Or it's the process of using balanced chemical reactions to determine the amount of products and reactants at the end of a chemical reaction given the mass of the reactants. All right. Does that sound fun? It's really like about a month, this stuff won't even bother you. The problem is you're at the start of your hike and it's a long way up, but it's not that bad in the long run. You have a nice view at the top. And it feels good. There's some sort of weird thing that goes on in your body when you get the right answer after a lot of work. It's cool. The problem is when you do all that work and you get the wrong answer, there's another feeling in your body, and I can't say that because I'm being recorded. All right. So, you don't need to write all this crap on the bottom, but if you have your ratios, like 2, 1, 2, it can get you from moles to moles, like 2 moles of Na to every 1 mole of Cl2. It can get you from grams to moles, like 117 grams of Na to, I did that one wrong, I remember now. This is the mass of NaCl, doubled, to 2 moles of NaCl. And you can go grams of one to grams another, but you first have to have these ratios. That's why it's super important to know how to balance a chemical reaction. All right, let me pass these out. The bottom one what? No, this one was fine. What I have here, what? Grams of Na would be 2 times its mass. 1 Na is 23, so I doubled it. NaCl is 58.5, but there's 2 of those, so I doubled that. So like it sort of makes sense, but don't write it down. I'm just showing that we can do these things if we use moles in the first place. All right, now, the way we're going to apply that for right now is we're going to find the formula from combustion analysis. It'll seem a little bit like it doesn't make any sense as far as relating it to what we just did, but it does. All right. So we were okay with finding them from percentages. We're going to add this wrinkle, find formula from combustion analysis, the rest of the hour. So combustion analysis is this. When in doubt, light the thing on fire. And that literally is what we are doing. Because when we combust something, it produces 2 products typically, carbon dioxide and water. We can analyze the CO2 and H2O produced to find out how much we had in the first place. It might make sense more with this slide. All right, so what we do is we have some sort of compound. And in this class, this compound will have C, H's, or O's, and occasionally an N. This process is used with organic compounds typically. So what we do is we light it on fire, and there's oxygen that can come into this chamber, and it burns. And it goes through this copper oxide section just to help the reaction go faster. And then it comes through here, and the water is absorbed, and you find out the change in mass. That tells you how much water was produced. And here the CO2 is absorbed, and that you calculate the mass to see how much of that was produced. And then you can do some math. And I want you to follow this idea here. Okay? So compounds containing CH and O are routinely analyzed through combustion in a chamber like this. The amount of C is determined from the mass of CO2 produced. I need you to get this part right here. The amount of CO2 that can be produced is dependent on how much C that you have in the first place, correct? Well, yes, but oxygen is part of the compound and the other reactant. So oxygen we're going to have to ignore. We'll find it a different way. But yes, that is true. All right, H is determined by the amount of water produced. And think about that. The only place H can come from is the amount of H you had at the start. Now let's apply what we just talked about and moles. Look at the screen for a second. How many C's, how many moles of C are there in 1 mole of CO2? 1. For every 1 C, we can produce 1 CO2. And those numbers are in moles. Now, H, for every 1 H I have, I can produce, I don't know why I wrote 1, 2 H2O. All right? Now, that doesn't seem to make sense, but remember, we might have a coefficient out front in the actual reaction, but the ratio here is 1 C to 1 CO2, all right, and 2 H's for every H. And it'll make sense, I think, as we go along. Now, O is determined a little bit different, because if you look up here, I might have something that's C, H, and O in here, but I have O coming from the outside as well. So we can't use O from CO2 or H2O. What we do is we determine it by finding the difference in the original mass to the masses of C, I should go here, and the masses of H. So follow here. If it's made out of C, H, and O, and I know how much C, I know how much H there is, if I know what I started with, the difference is the O. Okay. Complicated, but as we apply this one sinks in okay. All right, we ready for some application? Oh no. Don't do it to me. Don't. Usually this doesn't happen second hour. It happens first hour almost every day. But it didn't happen today. All right. We'll see here. All right. So this process, I know my writing is hard to read, but we're going to follow 4 simple steps. 2 of them are the same as what we already did. First, we convert mass of CO2 to moles of CO2. I'll walk you through that here in a minute. This part right here is called stoichiometry. Stoichiometry, look good? So is this one. Okay, so it's the idea of knowing what I have and finding something else using balanced chemical equations. So step 1, convert CO2 to C. Step 2, convert H2O to H. Step 3, divide by the smallest answer. We've done that before. And then write the formula. If O is present, it gets a lot more complicated, but we'll cross that bridge when we get there. So remember, we convert mass of CO2 to moles of C, mass of H2O to moles of H, divide by smallest number, and write the formula. And we're going to do that here in a second. Okay. So here we go. A 1.50 gram sample of a simple hydrocarbon. Oh, that's way down there. Hold on. I'll just leave it right like that. Simple hydrocarbon, by the way, means that it does not contain oxygen. That's what it will mean in this class. So it's only made out of 2 elements. And what are they? All right, carbon and hydrogen. That makes this much more simple. A 1.5 gram sample of a simple hydrocarbon undergoes complete combustion to produce this much CO2, this much H2O. What is the empirical formula of this compound? Please do this exactly how I do it. So the first thing you do, we're going to make what I call a picket fence. A picket fence is an organizational tool in chemistry to help you not screw up. You might like it, you might hate it, but just know that it's there to help you, not to ruin your life. So the picket fence works by putting what you're given first every single time. So I was given, remember my first step is to find C, right? So I was given 4.4 grams of CO2. Now, what these are, if you're in math class, these are just ratios that you put in parentheses and you multiply them. I just put them in this thing. I've had a lot of success with it. I used it. It makes things a lot more simple. All right, what we're solving for in that first step is just moles of C. Okay? So the way the picket fence works is we line things up until we eliminate the units that we don't want and we only have left the units that we do want. So here we go. In order to get rid of grams of CO2, where do I put them? On the bottom, so I go over and down. Whatever unit is here goes down over there. So I'm going to put grams of CO2. Right, now, as far as grams of CO2, I need to know what grams of CO2. So this step here, this is where you add the parts from the periodic table. We practiced that Friday. So this is 12 from the periodic table. This is 16. So I have 16 times 2 plus 12 is 44 grams. And anytime I write a number from the periodic table, it's always going to be per 1 mole of the same thing. We learned that Friday. The numbers listed up there are grams per mole. (44) came from the mass of carbon being a 12, the mass of oxygen being a 16, and there being 2 of them and 1 of them. So 32 plus 12 is 44. It's the numbers from the periodic table. All right, now, my answer is moles of C. Does this say moles of C? No, so I need to put mole CO2 on the bottom. Then on top, I'm going to put moles of C. Now, we're just looking at the formula for CO2. How many C's are in CO2? 1. So for every 1 CO2, I have 1 mole of C. Then I do some math. The picket fence is designed so that you multiply all the top numbers by each other, you multiply all the bottom numbers by each other, and then you divide your 2 answers. Now this is easy because there's 3 1s, and then this is obviously a tenth of that. So the answer here is 0.1. Yep, the left bottom is alone every single time but 1. We'll learn that in chapter 11, I think. All right. Now, what was the second step? Right here. Okay, we do the same thing, but now it's with H2O and H. So I have 2.7 grams of H2O. How many grams are there in water? Good. 18 grams H2O. And that's always listed as what? Okay, 1 mole of the same thing. But what am I solving for? So I need to get rid of mole H2O. So what do I do with that? All right, so every 1 mole H2O, how many H's do I have? 2 mole H. Because that 2 right there, right? No. Because I'm dividing this substance up. I'm not really doing a chemical reaction. I'm just saying what are the ratios of the 2 parts to each other. So the diatomic part was already there. All right, so now I take 2.7 and I multiply it by 2, and then I divide it by 18. And I didn't leave much room. The answer here is 0.3. All right, so now I have these two numbers. The next step in your instructions said to do what? All right, divide each one by the smallest of the answers. Which one's the smallest? 0.1, correct? So up here, this equals 1. And what does this equal? 3. So your overall formula, I should say empirical formula, is how many C's? 1. How many H's? CH3. To find their ratio. Hold on. Both these answers here are in moles, but I need to know the ratio of moles when I write my formula. So to know the ratio, I always divide them all by the lowest of them. Okay, now John? What? Okay, empirical means the lowest whole number ratio. So this is the empirical. This definitely would not be the answer, like for real. Like this is the answer of what I gave you. But more than likely, this is C2H6. But this is the molecular formula. This is the empirical formula. Now, by the way, it's super simple to find this. All that we would do, if we wanted the molecular formula, there would be one more sentence up here. All right, the rest of the problem would say, in a second experiment, the molar mass of this substance was found to be 45 grams per 1 mole. Okay? So it would have to give you that. So then you would look and you'd say, all right, well, what's the molar mass of this thing? 12 plus 3 is 15, right? Then you just have to say, what do I have to do to make 15 equal 45? Multiply it by 3. So we would say the molecular formula must be C3H9. We'll get there also. Like, I know this is a lot of stuff, but the last little part, that's not too bad. Okay. Let's do this one. This one, once again, is just C's and just H's. So go ahead, I'll pause this, but you guys take a few minutes and see if you can solve it. All right. So let's go ahead and work through this one now. So we have 0.845 grams CO2. Actually, I already had this all done, so why don't I just erase it? How many had it? It was a 1-to-1 ratio. Who didn't trust that? It's completely possible. Now, it probably is not C and H. It's probably C something and H something, but what do we know about the two somethings? They're the same number. This will be left as a 1-to-1 ratio. Well, we'll get in trouble if we round too often here. Like, for real, 44.0 something, 01 I think is what it added up to. But you should be pretty careful here. This it wouldn't matter because they were both the same answer. Go ahead, John. Right here for these, but this week that will be whatever number it feels like. But for combustion analysis, yes. I'll teach you, but not right now. All right, now, AP Chemistry is all about time saving. If you get this, then it's actually pretty fast. You take this number and divide it by 44. You take this number and you divide it by 9. The reason I divide it by 9 is because I divide it by 18 and multiply it by 2. Or I have 1 over 9, right? That would get you this same thing, and it would get you there pretty quickly. But if that didn't make sense to you, then don't do it that way. Okay, now we're going to find one with oxygen. So, well, first, look, if this is made out of CH and O, then we're in trouble because O is also one of the other reactants, right? So that's why we have to do it different. So first thing, you have this, it gives you an initial mass, it gives you all this, and asks what's the empirical formula. So the first thing I want you to do is convert your C's and your H's to moles again, and then stop after that. Try and do that pretty quick. It will, if you need oxygen, it will tell you that you need oxygen. So this one does tell you that it contains all of them. Now I'm going to do it pretty quick. If you don't want to see the answers, then don't look at them. Bless you. All right. Anyone have these answers yet? What was our moles of C equal to? 0.008. People agree with that? Okay. And what's our moles of H? Point what? 0.017? Yes and no. I honestly would never round it. I do it for speed in teaching, but the more accurate you are, the more accurate you'll be. And this, like the bigger the problem, the less you should round. We'll talk about that, but I'm going to run out of time. So, all right, now, then you should be fine. Okay. Now, don't do anything after this yet. You want to divide by the lowest number, and it's pretty obvious that it's a 2, right? 2 to 1. But don't go there yet, because oxygen might actually be a smaller number. Okay. So I have a little star here. These numbers are important, but we also need one other number. So now that we have these, we're going to multiply them by, I put them in a box for a reason. We're now going to multiply these by the mass of them. So what's the mass of carbon? 12. What's the mass of H? What's 8 times 12? That's 96. So 0.096, right? All right, now, these are grams. Now, you do not have to do this step unless you have to find oxygen. And probably in the next 3 minutes, this may not make sense for some of you. All right, to find oxygen, we have to find the total grams of C and H. So I add these together, and I get a number. What is that number? 0.113. All right, now stick with me. My initial mass is up here. So my initial mass is 0.2500. My mass of C and H is 0.113. The difference between these numbers will be my grams of oxygen. What did we get right here? Point what? All right. That is my grams of oxygen. So now I have to come down here and work another picket fence. 0.137 of oxygen. Now, I need moles of oxygen, so this one is shorter. I just have to divide it by its molar mass. 16 grams of oxygen for every 1 mole of oxygen. I got that from the initial mass it gave me. Okay, coming down here, I take this number and I divide it by 16. Anyone have that one yet? Okay, what? Oh, I don't like that. It's okay. All right. So now I have 3 numbers, right? These are the numbers that we find the lowest one and divide by. There were 2 zeros here, right? For sure. Okay. So this is the smallest one. So divide by 0.0085 and I get 1. Divide this by 0.0085 and I get 1. Oh, sorry. I'm assuming they were actually the same. Which they should. If we did our math better, they'd be the same number. I promise. What's this answer? 2. So last thing we have, the empirical CH2O. And by the way, this is sugar. This mysterious thing with sugar. Is sugar's formula CH2O? C6H12O6, but it's still a 1 to 2 to 1 ratio, right? So the rounding thing, that's why we got in a little trouble right there. Okay, don't worry. I don't expect the perfect knowledge of this right now, but I do soon.